Hello, I'm Alex Harris, and I'll be introducing my mech design project on shaft design and dynamic loads. Here we have the cover page for the mech design project of shaft design and dynamic loads. Summary: will given a stress history of dynamic loads, use the Goodman criteria to compute the factor of safety, and then apply a critical shaft frequency constraint to find the optimum factor of safety. Here's the table. It has the ultimate strength, yield strength, Poisson ratio, modulus of elasticity, density, shaft length, Newber constant, endurance limit. We will be using all of these in our calculations. We have the stress history for the dynamic loads for axial and shear, axial in blue and shear in red. We're able to take the alternating and mid-range stresses, and we can do that using MATLAB. You see in the code, you can find the max of the axial stress data and the max of the shear stress data, and same for the minimums. Using the max and mins, you can find the alternating axial stress and the mid-range axial stress, just in combination of A minus B over 2 and A plus B over 2 for alternating and mid-range in that order. Same for shear. You can find the same alternating stress and mid-range stress for shear. So I have my minimum diameter as 2.79 as I will go through this for loop. We'll have an if-else statement to account for the size factor. This will be done to get the most exact value. In doing this, we will also take account for the notch sensitivity using the Newber constant, and we will calculate the different fatigue factors, KF and KFS. What the size factor does is it modifies the endurance limit, and we use the modified endurance limit in our calculation for factor of safety. The equation for N is making use of the Goodman criteria, and we're just plugging in the alternating moment, the alternating torque, mid-range moment, and mid-range torque formulas to get the values. So now we're going to account for the critical shaft frequency, and we'll make sure we use it in hertz. This will be so we can apply our constraint to get a different data. But first we're going to look at the plots of factor of safety. At the top we have the plot for factor of safety versus diameter. The diameter is in millimeters, and we have a range from 0, about 2.79 to 250 plus. And we have the graph for critical shaft frequency versus diameter right here. As you can see, it's linear. As it moves up millimeters, the frequency gets there. So for our constraint, we want a omega greater than 150 hertz. In order to do that, we had to apply an optimization function. So we're going to look down at the MATLAB code. Here's the main MATLAB code. It's slowly what we've seen before. There's a couple extra calculations in there, but we're gonna jump over to the first function. We're gonna be trying in MATLAB function 5. You can see here we're gonna be maximizing. The factor of safety equation, which you can see is f of x equals that long function there at the bottom, and we're going to put that in our optimization function as well as the nonlinear constraint. First, it wants us to use optimization without the constraint, and I'll show you what that looks like in a second. Next, we'll have optimization with the constraint. So here's the constraint. It pretty much is the omega function. As you can see, the omega function is characterized by the c equals negative z times square root e to the I over m over 2 pi plus 150. That is your nonlinear constraint. You have the plus 150 and the minus the first part to get the the values greater than 150 is what we're looking for. 150 hertz, that is. So let's go back up to our main MATLAB code to where we can see the optimization function. So in the optimization code, we're going to guess around 5 millimeters and have our lower bound at 2.79 and our upper bound at 254. And then we're going to go use this function, the fmincon function, and we're going to call function 5 and function 6. Actually, to do what the project assigns right here is solve the optimum diameter when there's no constraint, a relaxed constraint. We're going to put, for our nonlinear constraint, we're just going to have it as an empty array, and that's going to get us a 2.79 millimeters optimum diameter and a factor of safety of 0.6938. Now, when we go back here to what you see in the MATLAB code, you'll have the code, the optimization code with the nonlinear constraint, which is function 6. At function 6 is included as a nonlinear constraint, and this gives us a some results. So this is our results with the constraint. We'll have an optimum diameter of 23.59695 millimeters and a factor of safety optimum of 0.6605, which is a little less than what we got without the constraint, but and the diameter is a little larger. So just looking at it, we know that the constraint cuts off the different diameters that are below 23.5965. That's kind of like the point of intersection. Kind of how it's almost where see these two plots. If you would put them on top of each other, it would intersect at like, let's see. With it's not exactly how that works, but it's when you put that constraint on this factor of safety function, the cutoff is around like 20. It says 23.5965 millimeters, as you can see in bold highlighted yellow. So our discussion is at around 23.6 millimeters is the best solution that we can get with the best factor of safety. And I believe like we did a pretty good job just wrapping everything up and getting these values. When I first did it, I tried it in meters and pascals. I found a better fit was when I used millimeters, megapascals, and kilograms was where I got the best fit and a smooth curve for this factor safety of first diameter. I think that concludes this presentation, but I hope you learned some more about shaft design and dynamic loads. So thank you for your time, and hope to see you all in class. Thank you. Bye.